This is a shortened presentation of Chapter 1 in the free astronomy textbook on Openstax website. I clarify that this is not the opening lecture, number 1, and it's not used for homework quiz 01. The real video lecture number 1 is a separate video called The Ancient Sky. I do this because I do not find introductory chapters satisfying. And actually, this is the typical case of my experience with almost all textbooks. I just don't find them relevant or interesting or well presented. And therefore, I built my own introductory lecture. So do not forget to watch the other video, the Ancient Sky video, okay? And remember, homework quiz number 1 is based upon the video Ancient Sky. Nevertheless, there are valuable information in this chapter, and I have made this presentation minimal, showing only the most relevant and helpful information. Let's start out with this gorgeous image taken by the Hubble Space Telescope. It is an image of a very small piece of sky. This is known as the Hubble Ultra Deep Field, and it is historically very important, setting the foundation for new generations of astronomy and the starting stage for cosmology. It looks like a collection of bright dots at first, but look carefully and you can see up to 10,000 galaxies, which with each galaxy holding about 1 billion stars. Now, I've seen an enlarged high-resolution version of this image, I believe, I remember in a conference, and it is just stunningly glorious, okay? There's so much detail you can study. You can see galaxies of different types, like big spirals, elliptical, and merging galaxies. And so let me just take this opportunity and go through this picture and get you interested. Obviously, you see the big galaxies right here. Look carefully, and you will see a nucleus in the middle and 2 spiral arms, okay? It's just very clear. Now, this one is a very good image of a galaxy, and obviously closer to us than others, okay? There's also other, maybe a galaxy not as well formed, but still looking pretty good, like a spiral galaxy. And sometimes you see galaxy edge on, like here, and showing you that galaxies are flat disks, like a frisbee or like a pizza. And let's see, if you look carefully, there is this very small galaxy with a ring structure around it. I don't know if you can see it, but look carefully. Is there? I can see it. And then there's maybe, like, for example, let's look at this one right here. Looks like 2 galaxies are interacting, and you can see the distortion of shapes right here. So these are merging galaxies, and I can see evidence of other mergers all everywhere, actually. You just look at 2 places. Let me see if I can find another one. Yeah, looks like, for example, in this region, okay, you can see there's really a lot going on. And among this, it looks like there are some interaction. So, gravity is pulling them together. And then this one is interesting. Okay, this object that looks like a mushroom. It looks like an active galaxy. Okay, you probably do not know what that means, but it's a galaxy that's acting up, right? And this one looks like a spherical galaxy here, and so on. And of course, there are other artifacts. For example, this guy right here, that's an artifact, and this guy right here, this is an artifact of the optics of the Hubble telescope. These are sort of the spikes, looks like a star, but they are not. These are not real. These are just artifacts. Okay, so just get you interested. It's a beautiful picture, and you can find these pictures online as well. This is called a Hubble Ultra Deep Field. Okay, and I'm sure James Webb is going to do similar things as well. Here is a definition or a description of what astronomy is, and it is defined as the study of the objects that lie beyond our planet Earth and the processes by which these objects interact with one another. I mean, that sounds pretty straightforward. But here, when we say processes, it means that we have to understand them, right? Otherwise, how do we know what processes are these? Okay, so even in that simple statement, there's really a lot of effort, such as understanding physics, that is already involved. Okay, and we will see, though, that it is much more, right? Of course, it is also humanity's attempt to organize what we learn into a clear history of the universe from the instant of its birth in the Big Bang to the present moment. And science is a progress report, one that changes constantly as new techniques and instruments allow us to probe the universe more deeply. And now this is a realistic and a what we call it a practicable perspective as we face the simple fact of not knowing everything. And maybe we can never know everything. Okay? And so before we know that supposedly existed everything, the ultimate truth, then how do we deal with the incomplete truth or the partial truth that we know of? Okay? So we select what we can or want to study. We make interpretations from what we can know. And we just try to peel the layers of this knowledge one by one, like peeling an onion. And each layer is different from the previous one. And so, in a practical term, as human endeavor, that's what science is. I mean, it describes our effort, not just science, not just the nature itself, right? It is what we do to interact with nature, how we study it, okay? But truth to be told, from my perspective, this seems to be true not just for science, but for many fields that are not science at all. Okay, so many fields are also dealing with developmental issue, finding their identity, and so on. So it's, to me, seems to be more of a universal truth and not just science. Now, I want to add the following four personal points as well. And the first is that science is often misinterpreted, okay, and interpreted as a particular school of thought. For example, in college we have school of science and a school of business and whatever. But in my perspective, science is really not that. Okay, sure, if we put in the human effort, we study academically. In that sense, it's the same as any other academic study. But science itself is ultimately simply about the description of nature, about finding out what's going on with nature. I mean, is there really any goal to it? What's the purpose of it? Well, it's really to just, to do it and to have knowledge, and really that's it. And so I don't see science as any school of thought or anything like that. If you inject the human aspect of it and say that's what we need to do, and from a human effort perspective, yes, you could interpret that way. But science itself, about nature, is really much more straightforward than that. Okay, and number two is that every field study faces human selection effect. So consistent with number one, we often interpret science or scientists in a certain way, but every field study, is sort of human bias in that sense. And an example is medical science will not focus on crickets, right? Medical science is all about human beings. We try to save ourselves, and we don't care about saving the crickets. And so, um, medical science is human centric, right? So there is a selection effect. Okay. Number three is science by nature is progressive and gets better. And that is, once a fact of science is established, it just doesn't change, right? And often there are people misunderstanding this as, oh, science can change. No, not in the way you think. It doesn't collapse. Something can change, like perspective, the model, but the physical principles, the facts, the established principles, they just don't change, right? And this leads to the next point: is what can change is what we call it the paradigm shift. All right. And this is one of the very important phrase or words that you should learn for your whole life. And I will point it out. I will give you some example of paradigm shift in this class. Okay, and one of the biggest one of the most important example in a historical example of paradigm shift is indeed the Copernicus revolution, when we move from the Earth center view to a Sun center view. All of a sudden, the way we understand the universe changed, right? Because of Copernicus revolution. But the physical principle hasn't changed. The data did not change. It is our view of the world, our understanding of it, and you can say our model of it changed, right? But it doesn't turn science upside down in the sense of data collapsing or physical principle change, right? Right? Does that make sense to you? And so I just want to make sure that as my students in this class, you understand some important aspects of science. Oh, by the way, I have one more personal example to add, and I think this can be very helpful. There is this very famous TV program host as an historian. His name is James Burke, and he was quite a big name in the 80s. Okay, and he had programs and like television series programs like Connections, The Day the Universe Changed, and many of us physicists, astronomy students were really into those programs, right? We talk about it a lot. Okay, so anyone of our age would know what I'm talking about, would know who James Burke is, and in fact, I learned a lot of the things from him that I'm teaching you right now, including how do you think about paradigm shift. I learned it from him. And one day he came to NASA, and I remember I was at Goddard, and I was attending his talk, and of course he was very, very exciting to listen to, and he was referring to about his history, about how we think about history, and he made a comment about Carl Sagan. He says whether he was talking to Carl Sagan or maybe he was just watching Carl Sagan. Of course, Carl Sagan is this famous astronomer. Okay, if you don't know, you can look him up. He's a big time personality, right? And because Carl Sagan said, for example, Ptolemy was wrong, and of course, if you know Ptolemy, we're talking about the Earth center model, okay? And so Carl Sagan makes some comments like, Ptolemy was wrong. We're not in an Earth center model. Something of that to that effect. And James Burke in the talk made it clear. I mean, you could say it that way, but Ptolemy wasn't wrong. He was right in his context. Yes, he's not correct by the current understanding, but at his time, everything he did was right and consistent with what he saw, right? And so you really cannot say that he was wrong, because if you're going to say that he was wrong, then everyone was wrong before. Newton was wrong. Eventually, Einstein would be wrong. Everybody would be wrong. So such a statement would be really, really not helpful, right? It doesn't really communicate really what is going on in terms of progress of science, right? We're talking about models here, okay? Model is about making it consistent with what we saw and making it work at the time until a better model comes along and supersede it, right? And so I think this is a very important perspective to think about. Not so and so was wrong. It's not that Ptolemy is wrong or the people before Newton were wrong. They were right in their context. They did their best, and these models work. In fact, I just talked about this in the video Ancient Sky, that the concept of the celestial sphere, of course, is far from reality. It cannot be farther from the truth of what the universe really is. And yet, the celestial sphere is a perfectly working model in which we still use today. You can still go on Amazon and buy a celestial sphere to work with for the observation of the night sky. So how can that be wrong, right? And so just keep that in mind. Models for doing any times are right in their context, and it can still be useful. Okay? Okay, so let's move on to numbers in astronomy. And a scientific notation is a convenient way of expressing very large and very small numbers. And this is especially true and useful for astronomy because astronomy spans the widest scales of all sciences, right? From the smallest uh, subatomic particles that we need to study to the entire scale of the universe, right? This is the widest range uh, of scientific number possible. If you compare that to geology, you can argue it's at most millimeter to about maybe 10 kilometers, right? And that's geological scale. Definitely nothing like astronomy, right? So we definitely do not want to write large number a lot, let's say 1 followed by 30 zero or even 100 zeros. We don't want to do that. And this is where scientific notation comes in handy. And let's give an example. And so let's say 1 billion. Let's just look at 1 billion here. And is 1, okay? 1 followed by 9 0. And you count to 9. The way you do this counting, I'm sure you learned this in high school. You start out with the decimal place, and you do a placement. 1, 2, 3, 4, 5, 6, 7, 8, 9, until you reach to the right of 1. So 9 places. And so 1 times 10 to the 9. And same thing for similar for numbers smaller than 1. Let's look at this number right here, 0.001. You start out with the decimal place, and then you move 1, 2, 3, okay, to the right of 1. And so you write as 1 times 10 to the minus 3. Now, I want to point out, these are not just compact notation. They are not just efficient way of writing. They are formal and rigorous mathematics that you can work with these scientific notation and the power to make it extremely easy. All right. So, but it's not something that we do. Hopefully you've learned that. But the important things to understand is that even though this course is not supposed to be use math a lot, nevertheless, when we are talking about astronomical numbers, you will see these numbers that are very small, very large. So you have to get used to them anyway. Okay, so here is a question. The age of the universe is estimated to be 138,000,000 years old. Okay, of course, some of you are pretty smart. Maybe you understand that this is basically 13.8 billions. So how do you write this? Well, then you follow the rule, okay, and then you go 1, 2, 3, and so on, all the way to here, okay? I will not finish the counting, all the way to this point right here, to the right of 1. And then you will count that as 10, okay? So it's 1.38 times 10 to the 10. But often in astronomy, we like to write 13.8 times 10 to the 9. And that's because we like to say 13.8 billion years. It's just a way, it's easier way to write it. So we can write 1.38 times 10 to the 10, the official scientific notation, or we can be a little bit more flexible just for the purpose of easier communication. We can say 13.8 times 10 to the 9, which is 13.8 billion years old. And you will hear that more often, okay? But anyway, for this answer, it's E. Okay, this slide is titled Our Place in a Universe, but it's about the distance scale and how large this universe is. Distances in astronomy are large, so it is also intelligent and wise to use a distance scale that is also quite large, not like a meter. And a light year is a distance that light can travel in 1 year. Okay, so a light year sounds like time, but it's just a term to describe the distance. Okay, it's a distance scale that light can travel in 1 year. And it is about 10 trillion, which is 1 followed by 13 zeros, kilometers, okay? Or 6 trillion miles. So just imagine, instead of saying 10 trillion kilometers, right? Just how awful that is to say, or even when you try to write it down. And so it is wise to have something very simple, just LY, 1 light year, okay? It's a good choice. By the way, another similar distance scale is a parsec, and you will learn about it in this course. In this course, we will talk about the local coordinate or the local sky repeatedly. And here is a quick presentation of the visual, not about a coordinate, but just to describe what you see. And so when you look, here you stand, okay, here you are standing. Wherever you are, you look up, and there is directly above you is the zenith, okay? And horizon is this imaginary line separating the land and the sky, okay? And horizon is a good reference point for the angular angle or altitude. For example, you look at an object here. Let's say here is a star. Okay, here's a star, right? And you want to say the angle with respect to the horizon. Okay, this angle right here. Okay, this angle right here is called the altitude, right? Is from the horizon here all the way to this mark right here, okay? And often astronomers will use the word like height very loosely, okay? So I remember when I first learning astronomy, I get a little confused. So often astronomers, when they use the word height, in this context, they actually mean angle, okay? They don't mean, and when they say distance, sometimes they also mean angle. They don't really mean the actual physical distance like kilometer. They actually mean degrees, okay? And so there's also oh, by the way, let me label this. This is altitude, ALT, okay? But there's also the azimuth angle, right? So let's pretend this is north right here. This direction is north, okay? And therefore you're looking at North Star this direction. And so the east direction or the westward direction, this way you're looking the east, going left or right, moving left or right. That's the azimuth angle, all right? So there's the altitude, and then there's the azimuth. These two angles defines the two angular coordinates of your local sky. So with these two angular coordinates, the altitude and azimuth, you can specify an object's location in the local sky on the sky map, okay? Remember that the sky is basically a two-dimensional object. It's a two-dimensional sphere. So you just need two angles, okay, not three. And for example, you say, I see Saturn altitude 75 degrees, which means is 75 degrees north, okay, upward of a horizon, and it is at azimuth 165 degree. And keep in mind that very commonly we use the North Star, the north direction, to be the reference point for the 0 degree azimuth, which means that Saturn 165 degrees is almost opposite, right, in the opposite direction to North Star, okay, because it's almost 180. Okay, now we are moving on to so-called backyard astronomy, right? How to read a star map. And as an amateur stargazer, you will need to know how to read this star map. And the easiest way that I can explain this to you, and just really just once, there's no other way that I think is better, is to just imagine yourself uh, in a field out there, looking up towards the sky. And the sky, of course, to you will appear like a dome above you, right? Like a dome. And another way you can think about this in equivalent way is to imagine yourself in the middle of a half-domed planetarium, right? And planetarium is supposed to simulate the sky. So it's the same, whether you're looking up inside a planetarium or you're looking at the actual evening sky, what you are seeing is 360 degrees all around you and a half dome above you. All right. So first visualize that. Okay. And then imagine this flat map in front of you representing that half dome view that you see. And so this flat map in front of you that we are looking at on the screen is a two-dimensional flat representation of that half dome. Okay? Does that make sense to you? So close your eye and just imagine you are inside that planetarium. And let's say you start out north. And then you just, rotate 90 degrees towards west. And then you just rotate another 90 degrees towards south. And then rotates another 90 degrees towards east. And so on. And then just imagine as you do this 360 degrees sort of move, rotating around, what kind of sky you will see above you, how the sky change. And this is what you will see of the star map, right? The star map is a projection of that. And that's the best way I can explain it. And so, maybe there are other ways, but I'm not so sure they are better than what is just presented to you. You have to be able to visualize it, okay? So again, visualize yourself inside, in the middle of a planetarium, okay? Planetarium. And then visualize until you get this map. And by the way, let me point out some of the thing. Here is a zenith right here, right in the middle, right? Because you are right in the middle of the planetarium. You're looking directly up, right? And that's where it is, right? You are right. The zenith is right here. Horizon is all this 360 degree all around right here. That's your horizon. That's the ground. That's that line between the ground and the sky. And let's look at some famous stars. In fact, just one. And I'm just going to look at this and say, see, I recognize, and that's Polaris. And in fact, just by this star map and look at this distance, I can sort of kind of a guess, make a guess of where this map is based upon, right? Just because, you will learn later on that there is a correlation between your location and the altitude or how far it is from horizon. That is Polaris. Then how do I know it's Polaris? And that's because I know there is this big bear right here. This is Ursa Major, right? In fact, it looks like a spoon to me, right? Like a ladle. And if you look at this two star right here, and you see this two star points towards, right? There's this pointing like this, right? That's one way to locate Polaris. You look at Ursa Major and locate that two stars right at the front of the ladle. And that direction points towards Polaris. And by the way, Polaris itself is bright enough. Often you can just recognize it without the help, without trying to find Ursa Major. But sometimes it's a little bit dim. So finding Ursa Major helps. The general direction to read a star map is actually quite straightforward. Whatever direction you are facing, let's say north, then you rotate and hold the star map so that you can read the word north at the bottom, right? And so if you're facing south, then you need to hold it so that you are facing, you can read the word south at the bottom. So basically, you just have to adjust your direction, whichever you're looking at, whichever direction you're looking at, make sure the direction, whatever the direction is on that map is on the bottom, right? Because, the bottom of that star map is represent the horizon you are actually looking at. I mean, it's very straightforward. And by the way, star map, of course, depends on location, right? I mean, imagine someone in North Pole versus someone in Singapore, right? They're gonna look at the sky very differently. But however, it gives you a sense of the scale of the entire Earth. Even Miami and Boston, two cities that you think are very far away from one another in the United States, more or less can get away by using the same map, right? Because even though you think of United States as this huge country, but on the scale of the Earth, it's actually quite a tiny fraction. And so a star map for Miami and a star map from Boston have little differences, but not by much. All right, so you can actually get away with using the same map. You can see the differences, but not much. So again, this is the question that you can use for discussion. Repeat, you can use this question for discussion, even though it is not explicitly listed in the discussion instruction in Blackboard. All right, so sometimes I do this. I give you some sort of extra question or extra bonus for discussion without mentioning it explicitly in the discussion instruction. And this is because I'm encouraging people to watch my video, right? And if you do this, just say, oh, answering the video question, which constellation would you see so and so? But do not mention the word bonus or whatever, anything like that, because I'm inclined to give you a bonus, all right? And so on. And so next question, what constellation would you see at your zenith? Same thing, okay? Just don't mention the word bonus or anything. Just answer the question in a very non-confusing way, but don't reveal the word bonus. Just say, oh, in answering the question from the lecture, I see this constellation, so and so, and so and so, and this is the reason why. Make sure you explain it. By the way, don't just give answers. A lot of students make the mistake of saying, oh, the answer is this, and then they get a low score, and they don't understand why. Remember, you're not providing answers. You are providing discussions. So you must discuss. Okay? Pound this into your head. You must discuss. All right, this is the end of the lecture.